Okay, welcome everybody. Good afternoon or good evening, good morning, wherever you are. It's great to have you on, this is day 12 of our climate summit. And today we are going to be talking about climate and what is happening because of the COVID-19 lockdowns specifically. And I have with me an expert on this topic from Harvard, Dr. Tao. And Dr. Tao has been looking at the global dimming effect, but what aerosols that we emit has been doing, and the impact of eliminating aerosols, which is pretty much, what we are doing now is as the industrial activities decline, there's not enough aerosols being pumped up into the atmosphere, and aerosols only stay there for 4 to 5 days, right? So it is causing, I mean, we see things being very bright already from an empirical perspective. So I'm glad that Dr. Tao is able to join us to have a conversation about this, that we can get to the bottom of it and understand the impact of what we are doing and what solution we have, to address that. So thank you very much for joining us, Dr. Tao.
Yeah, thank you for the invitation. Point of clarification, so my specialty is not exactly just focused on studying aerosols.
Right.
So I'm a chemist, physicist by training, and I'm predominantly an experimentalist. So
okay.
My group, we're developing instrumentation and new methods, new machines to accomplish different tasks, like to make new materials or to enable new kinds of physical measurements. So that's our forte. Okay. And the climate science and the solutions, it's something that that uses the same kind of tool set, if you will, right, but to just apply it to a slightly different set of problems. So, my contribution to understanding the climate has so far been, first of all, to really examine the problem from a systems perspective. Everything in climate is connected. The trees, the oceans, the humans, the food we produce, the wars we engage in, right, and the psychological problems that we're suffering from as a result of climate change. Right? So everything is connected, but because of this interconnection and the vast number of fields that that it affects, it's a very challenging problem because of the sheer size of the problem. But it has been possible through a more like global analysis of the literature to distill out the key stressors and physical variables that's really causing the problem. And if we take more of a global perspective, top-down analysis, that's how potential solutions can arise. And we believe to have gained such understanding of a promising approach to the problem. Right. And I think today the focus is on, well, you mentioned the potential effect of COVID-19 on the climate situation. So, right. So I prepared some slides, not exactly targeting that problem, but I will mention a few words at the end to that effect. But I'd like to share with the audience perhaps to go a little bit deeper into the dominant threat that we as a civilization, as a planet, that we're facing. So this threat overshadows all the other problems we face, be it economic downturn, be it local limited war, or mass migration. It could be related, but the threat of planetary heating overshadows everything, overshadows the ocean plastic problem, overshadows human rights problem on the temporal scale. That's important. Of course, many of these problems are important, but if we cannot, say, keep the civilization running for the next, beyond the next 10 years, then it's pointless to talk about many other problems. So let's maybe get into the presentation. I prepared some slides. It may take some a bit longer than expected, but let's see.
Sure.
So I should be able to share screens, right?
Yeah. Under meeting, you should be able to click on meeting. And
yeah. hope it's this one. Does it just share the, if I just say start the
you should be able to say
presentation.
start share. There should be a start share.
Oh, okay.
There you go.
Okay, but it's a different one that I wanted. Wait a second. If I just start a presentation, maybe it automatically chooses that one. From current slide. Can you guys see this?
Now we see you now.
Oh.
So you have to, under meeting, on the Zoom menu, under meeting, there is a start screen share.
Yes.
Or at the bottom, there should be one that says, it's a green button saying share screen.
Yes, I'm in there, but it brings up the wrong. I think I have too many presentation files open. Let me put down. Okay. Let's have 3.
I mean, we can also do this as a conversation if you want. If it's, this is the problem.
Also, if you have multiple presentations.
Do you see this or no?
You need to go back to screen share because we're seeing you. And then once you share your screen, then you can select the presentation that you want us to see. Right now, we're seeing the one that starts with the recap of previous presentations.
So you can go under File and open the right.
Do you see that? Is
yeah,
that
we see that.
maximized? Okay.
Yeah.
All right. So for viewers who are watching like this topic for the first time, I suggest going to those 3 links to get to learn about the basics. So because I won't have the time to cover everything again, so we will just give a recap of what was talked about in those 3 presentations. So basically, we used a reanalysis of historical data on temperature and the CO2 to show that there's no denial that anthropogenic climate change is real and perfectly and definitely driven by human emissions. We also noted that contrary to popular belief, it's actually not possible to let go of the fossil fuel industry as of now because of a side effect of the aerosols that Salish mentioned already. And those presentations also discuss why, as a result, partially as a result of the aerosol dimming effect, renewable energies, regardless of how quickly and to what extent they're implemented, are not sufficient to stop the climate crisis. And we also touched on, but didn't really explore in detail, why natural solutions, including planting trees, are not solutions, and actually they are usually just physically not possible to implement. So today we will focus on the dominant driver and threat to Earth, namely planetary overheating. And we will also briefly have a conversation about whether local personal adaptation level efforts are effective or enough to turn the ship around. So here's a recap from a previous presentation plotting historical data of the CO2 concentration in the atmosphere and the global average surface temperature. And the color coding is based on a logarithmic color coding. So the red and up to yellow points denote recent history when humans started to burn fossil fuel. So from this kind of analysis, it's clear that the perturbation that we are inducing to the planet by burning fossil fuel is certainly not part of natural variability that the Earth underwent over the past 1 million years or so. And we discussed in previous presentations why current trajectory that we're subjecting the Earth system to is projected to bring the whole ecosystem outside of range that's compatible with life as we know it on this planet. And we briefly mentioned the reasons for different boundaries on the CO2 axis, and also experimental evidence, selected evidence that we cannot really let average temperature cross over 2 degrees Celsius. And over 3 degrees Celsius, we're projecting a catastrophic meltdown of most complex ecosystems. And the unfortunate thing is that without any modeling, just based on historical data in the past decades, and assume linear projection, not even exponential growth, as economists would like us to achieve, we are well on track to surpassing those hard physical, biological limits within the next decade or two. And analysis along those two dimensions shows that the first boundary we're crossing is obviously the temperature boundary, and that's coming up within the next 10 to 20 years at most. And the intrinsic tolerance of ecosystems to CO2 levels, carbon dioxide, if we are able to remove temperature, would only become problematic more than a century from now. So that's actually a good news. That means if somehow we can remove the temperature effect, we can still rely on an efficient source of energy to make the transition that we need in order to establish a new type of equilibrium in the future. So now I'd like to, so we finished a recap, and I'd like to talk about a bit more in detail mechanisms of why temperature is such a universal determinant of ecosystem and life performance. So in this conceptual diagram, we're plotting a bunch of curves as a function of the temperature. And on the y-axis, it's labeled aerobic metabolism. So we know we're talking about some living animals, a system that can metabolize and produce energy and using oxygen. Let's focus first on the black curve. The black curve are sort of like exponentially growing. It denotes the amount of oxygen usage by some animal as a function of temperature. So like, you guys can interrupt me if you have questions. But as temperature increases, our enzymes work faster. Our metabolism increases in rate. So we need to take in more oxygen in order to satisfy a basal demand for energy conversion and the maintenance. So the black curve denotes the minimum amount of energy our body needs to produce by burning up fuel using oxygen, oxidative process to produce that energy. Now let's focus on the red curve, the solid red curve. That curve denotes how much oxygen we can process in the most optimal case. So for example, in COVID patients, their ability to assimilate oxygen decreases. So that curve would go down. But in general, for animals, there's an optimal temperature where this curve reaches a maximum. And where that maximum occurs depends on the life history and evolutionary history of that particular species and life history of the individual. But it's quite general among organisms, animals, that there's this maximum. Then the difference between how much oxygen you can assimilate and how much oxygen you need to barely survive, so that's the green double-headed arrow, denotes how much excess energy you have to perform other lively functions, including growing, breeding, and reproducing. So that's the basic function or goal of organisms. And we can see that the resulting green curve also has this inverted bell shape, reaching maximum, but then decaying quickly as temperature increases. And there are also many organisms that have a sharper decrease, as denoted by the dotted green line. But regardless of the specifics of the functional shape, this inverted bell shape is common in animals. It turns out that this kind of trend is also general for plants. And example includes, say, the green data points denoting the efficiency of photosynthesis also shows this inverted curve. And in general, for crops and plants in general, for each day above 30 degrees. So you can see that 30 degrees is roughly where the curve inverts. For every day of exposure above 30 degrees by 1 degree, we have roughly 1% decrease in crop yield. So that sort of makes sense. And the curve goes even, can even be generalized to viruses and bacteria, even though the intrinsic mechanism may be different. But just goes to show that practically all life on Earth is subjected to this control by temperature. And there's an optimal range of temperature that each individual needs to stay within in order to thrive. And in general, the fall off at the high temperature end is very steep. So a degree or two excursion beyond what's normal or optimal will lead to tragic consequences for the individual and communities. And so this paper basically tries to analyze the performance of animals given this universal inverted and skewed bell curve. We will not go into details for this audience. I think details could be, a more detailed discussion could be found in one of the previous talks. But suffice to say that the increase in the mean of the average temperature or the average of temperature, or the increase in the variance, basically how erratic temperature changes, either of those would lead to a decrease in performance. And that's what's happening on Earth in the past 50 years or so. So I think the green curve denotes the weather or the weather pattern in the northern hemisphere in the 1950s, and the colored data points are data from 2011, I think. So we see that for one, the ensemble of temperature measurements, it's shifting toward warmer temperatures by the mean more than 1 degree Celsius. And also it's widening. It's becoming, the peak is becoming lower. It's another way of saying it's becoming, the variance is larger. So weather patterns are more erratic. So both of those trends are bad news for ecosystem performance based on a very simple theoretical expectation. All right, let's skip that. All right, so let's look at some examples of why heat is a dominant, a universal disruptor for many different types of systems and ecosystems on Earth. So we'll talk about marine, terrestrial, and humans. So there, in the recent decades, things about 2003, based on this mini review, there have been quite a few episodes of marine heat waves. So these events are defined as periods of over several days, often weeks or months, during which the water temperature exceeds, say, the average by a couple standard deviations of what's considered normal. So basically, warm water temperatures that are unlikely to happen by random chance. And if those periods last for extended period of time of days to weeks, then they can be considered as a marine heat wave. And by today, roughly 90% of marine heat waves that are occurring around the globe can be attributed to human activities. Just a sidetrack, the science of attribution is still a quite young field in climate science. So basically the question is, given an extreme event, say a hurricane, with what confidence do we know that it would not have happened if climate change didn't occur? So this field is fairly young, but it's becoming quite predictive. And I think in the next year or so, maybe even weather forecasts would be able to tell you whether the extreme heat tomorrow or the freezing cold coming next Thursday could be climate related. So that's an active area of research. So that's a digression. But right now we already know with high confidence that 90% of these marine heat waves are attributed to human activities. And the consequence of these marine heat waves are quite catastrophic for sea creatures, as documented in several publications to that effect. I think I wasn't in the US during that time, but I've talked to colleagues at my institute who experienced that episode when they were studying at Stanford. And so organisms can just perish from direct heat exposure, as in the case of those little arthropods, or they could also die indirectly, as in the case of these puffins. So what happened to these birds was not that they got a heat stroke. They died because of malnutrition. And the reason why they got malnutrition was because the warm ocean drove a population of prey, little tiny fish from equatorial regions up to northern regions. And this particular species was not as nutritious as the natural prey of these birds. But unable to distinguish between the different foods, they ate the wrong food that was less nutritious. And as a result, they couldn't make through migrations or winter or subsequent periods of food shortage. So it's an indirect way to die from a marine heat wave. Just another example to show the interconnectedness of ecosystems. So the bad news for marine ecosystems is that we are well on track to see another effect of average 5 to 10 increase in the duration, frequency, and severity of these marine heat wave events. So if we keep on emitting as we have been so far, by mid-century, we're looking at annual mean duration that's 50 days. So that's like a couple months, 60 days of just extended warming. Those sort of heating will be very catastrophic for fisheries of many types. And here we're just reiterating why the sea is very sensitive to the warming. So on the left, we're looking at the energy content of the ocean since the past 80 years or so. Compared to the temperature trend, we see it's a lot less noise, right? And the reason is because water has a much larger heat capacity. So small variance excursions in temperature doesn't really get captured instantaneously by virtue of the thermal capacity or thermal inertia of the ocean. So it basically filters out the noise. That's why we see a very clear trend of energy increasing. And just to make one point that's tangential. So that amount of energy that we're depositing into the ocean via greenhouse effect is equal to like 500 years of what we actually use. So it reiterates the inefficiency of fossil fuel as a source, as a fuel, if we take into account secondary, or in this case, dramatic consequences for ecosystems. So we are using 1 joule, but we're causing indirectly accumulation of, say, 100 joules of waste energy dumped into ecosystem. And on the right, it's a conceptual illustration of why ocean marine ecosystems are especially prone to having these marine heat waves and catastrophic events. Not because the sea is warming faster than land, but in fact, the ocean is warming less quickly than land because of, again, the thermal capacity is bigger and it's slower. But for the same shift in mean, because the variance is smaller, the part that's extending beyond historical expectation values is substantially bigger for marine heat waves. All right. So here's an example of a marine heat wave that occurred in parts of Australia, and its consequences for the coral community. And so there are a lot of efforts trying to save the corals. People have tried all sorts of ideas, and right now it's widely recognized that if we don't get the temperature parameter under control, it's basically a Herculean task that will not ever be effective, because one of these events will wipe out years to decades of restoration efforts. So that's, I think, the last example for marine. So algae are also devastated by heat waves. So on the right, you see a temperature record over about 2 years. And between 2017 and 2018, you see a couple spikes that's protruding above the previous summer in 2016. And that excursion in temperature is on the order of a couple degrees. So that's another example of why a couple degrees may not feel like much, but on the ecosystem impact and in the context of these extreme events that happens for very quickly for a day or two is sufficient to completely destroy and annihilate the natural world that we depend on. Okay, let's turn to land briefly. So in the restoration and eco community, there's a lot of effort trying to plant trees or use natural solutions to reverse climate devastation. So the following slides are to give a qualitative discussion of why such efforts are in vain, unfortunately, and are not likely to be effective, even if the entire world's energy were devoted to such tasks. So the basic problem is that one can determine whether a region is suitable for forests by looking at the annual trends in temperature and precipitation patterns. And these parameters can be very well predicted based on our current knowledge of the trajectory of the atmosphere and its interaction with the various variables, including solar irradiation and aerosols. And the prediction is that the area that's suitable for planting trees will inevitably become smaller and smaller and smaller as we go into the future. So that basically means the effort involved to keep trees artificially alive would increase substantially. And I really like this graph on the right that the authors used to illustrate this effect. So it's reminiscent of, okay, sorry, I cropped out the somehow the x-axis. It should be moisture, basically rainfall on the x-axis. So there's a region that's suitable for trees, denoted by the green circle. But if we warm up the climate, we move up into more of a region where most of the surface area becomes inhospitable to trees. The same if we go into extremes in moisture, in drought. And unfortunately, the future trend is one of increasing difficulty to keep forests alive. So we need to focus on keeping what we have, make sure that we leave them alone, and in order to preserve as much biodiversity as possible, but we should not invest efforts in fighting a lost fight, because doing so would distract from more efficient and effective solutions that may eventually enable a fuller restoration effort. So these are just some example pictures of patches of forests that are already dying. That's data roughly 10 years ago or more. So the devastation, as we now know, in parts of Central America and in Australia is orders of magnitude more extensive. So the trend continues. Okay, and lastly, let's talk about the effect of temperature, just this variable alone, on human societies. This topic has been discussed for the last decades. The question is whether temperature is a useful predictor of conflict occurrence, frequency, severity in human systems. And the synthesis of available literature suggests that it's a significant factor, may not be the direct factor in most cases, but certainly at least an indirect factor through different mechanisms, most prominent being crop failure induced migration that we have borne witness to in the past decade or so. There's also substantial literature on how mental health is correlated with temperature. And we also become dumber when temperature gets very warm. So for students studying at home and taking finals, take-home finals, I suggest at least turn on your AC during your exam period. So the effect is quite, in some cases, quite dramatic. And some authors noted that previous collapse of human civilizations in all continents can be quite robustly linked to periods of temperature fluctuation and the drought induced by temperature fluctuation. All right, so I wasn't sure whether the audience was aware of the aerosol masking effect, so I put in a few slides. So maybe we'll go through it fairly quickly. So at the same time that we burn fossil fuel, we also unwittingly emit other compounds, including sulfur dioxide and black carbon and nitrogen oxides. And these chemicals interact in the atmosphere under sunlight irradiation. They aggregate and polymerize sometimes and create particles that can scatter away shortwave radiation, sometimes also trapping longwave radiations. But the net effect of these secondary particles formed by our emissions is a cooling. So the net effect is a quite substantial cooling. at the level of 1.6 plus minus 0.2 watts per square meter. And watt per square meter forcing can be translated into a temperature change by climate sensitivity. So people have some disagreement over this value, maybe up to a factor of 1.5 or 2 at most. But in my personal opinion, being an experimentalist, I really trust historical data. So paper published last year by Snyder used historical data on Earth, and this experimental value of 0.84 suggests that if we were to let go of the aerosols, we're looking at more than 1 degree Celsius of global temperature rise. And so here are a list of publications for readers that are interested in learning more about the subject. And so the existence of this effect, which for some unknown reason is almost censored in public discourse, means that the dream of stopping at 1.5 degrees or even 2 degrees are just dreams, because even by the end of 2005, if we had stopped all emissions by the end of 2005 and let the ecosystem equilibrate to its final equilibrium temperature, we would still be looking at, with high probability, above 2 degrees of warming. So that's 15 years ago. And now we have continued to emit more. So now we're looking at least maybe 4 or more degrees Celsius if we were to stop emission completely today. And so now let's discuss a paper in anticipation to perhaps a discussion on the effect of COVID-19 on global climate in the coming year or so. So these researchers ask the question of what happens if, say, one of the major economies stopped emitting. So let's look at the column on the left. So here they're plotting temperature change as a result of different parts of the world stop emitting sulfur dioxide. So on panel A, it's if the US stopped emitting, it's roughly 18 teragrams of sulfur dioxide per year. We're looking at, based on the scale bar, roughly like half a degree Celsius rise in temperature over most of the inhabited world. The Arctic, in all cases, seems to be especially sensitive to this unmasking, reaching consistently about 1 degree Celsius rise, just when one particular region shuts down, the US. Second row, D, that if the European Union shut down, it's basically the same result, right? And very interestingly, when China shuts down, the effect seems to be less. So if anybody is gonna clean up their air, I think China can do so with the least penalty for the rest of the world. So that's just interesting. And India shutting down leads to comparable warming than China, even though it's a smaller amount of removed as sulfur dioxide. All right, so on the left, we have mean temperature change. But of course, as we discussed before, what really kills ecosystems and animals are these extreme temperatures, right? Humans, we can probably survive at 33 degrees, 34 degrees just fine, not very comfortably, but we won't die. But if temperature went to 42 for an hour or two, then we're dead. So because we're basically already very advanced in this global warming endeavor, what's really dangerous are these extreme events. So on the right side, we have the occurrence of extreme events as a result of the different local reduction in this aerosol. And it's, in this case, removing sulfur dioxide from the US will cause a dramatic impact to the US in terms of extreme temperatures, and similarly to EU. But somehow for China, the same reduction doesn't lead to as severe extreme temperature impact as removal from the other sources. And in this paper, just it's a side result. Their derived climate sensitivity is in agreement with what the Snyder used or Snyder found through empirical data. So this one is a more of a computational study. The previous one was experimental. So the two agree. Of course, there's thousands of studies of the sort. I'm just presenting selected paper with decent graphics for the lay audience. So here is another study basically reiterating the same message, that if we are to, first of all, continue our emissions 10 to 30 years later, a large part of the currently inhabited world will utterly become deadly to human life. We're looking at up to 2 to 3 degrees Celsius rise in large parts of Africa, Brazil and India, and South Asia and Northern Australia. So I think this study, their question was, what's the relative benefit of, say, reducing carbon versus continuing emission, but also making sure that the aerosols are emitted. So on the left, that's how much cooling we have relative to that catastrophic world of RCP 8.5 if we were to decrease our emissions following RCP 4.5. We see that we get a respite of about maybe 0.5 degrees Celsius, which means it's still too hot, right? But it's some cooling if we were to reduce our emissions. But let's say if we were to make sure that in that emission scenario, we do not remove what's causing the smogs, the pollution, we get comparable cooling effect, even if we were to continue the emission. So that just is an example that underlines how important it is at this point late in the game to keep burning dirty coal and dirty fossil fuels. And this graph compares the relative impact or relative effectiveness of masking using dirty emissions versus reducing emissions. One means the aerosols is 2 times as effective as reducing CO2 emissions to RCP 4.5, and -1 means, let me think, means it's, I think, the other way. It's just how the authors chose to compute that parameter. But the take-home message is that for most of Northern Hemisphere, where most people live, reducing CO2 emission is less effective than keeping the air dirty to avoid the worst of heating. And here is this effect not on the mean temperature as on the previous slide, but on extreme temperatures. So the column or data to focus on are the data on the right side. So these are the relative effectiveness of aerosol cooling versus straight up reducing CO2 emissions. So again, for most of the inhabited world, it's much better to keep on burning dirty coal than to reduce emissions. Here are papers on projections of future extreme heat events and its impact on human migration and societies for people who have access to these journals and libraries. Okay, so I think finally it's just curious because China's economy was shut down, I don't know, late December through maybe still only partially up and running. But according to an OAA, Asia experienced the warmest January on record. And then again, the warmest February on record. These are observations that are not proof, of course, of aerosol masking, but they're consistent with this phenomenon. But of course, whether there's a linkage, direct linkage, needs further analysis by people in the attribution science field, right? And lastly, let's give me a minute. So how are we doing on time, Silish? I don't want to.
We have to wrap up quickly because I have some questions from what you've already asked.
Okay. Okay. So I will very quickly talk about one example of local efforts. So that with regard to coral reefs, which we mentioned before. Actually, I will just skip over this. So the take-home message is that people compared whether coral recover better or or suffer less loss as a result of banning fishing in those areas. But the overwhelming result from those studies is that no, there's no difference. What really matters is when there's a thermal event like El Nino, that's when everything collapses. Everything else doesn't really make an impact or minor impact. So people can go to the reference. Yeah, and again, so to put our to extend this conceptual drawing of some authors, the elephant in the room is the heat, the temperature, and that's the dominant driver. So no matter how much effort you put into the other interventions, if you can't get the dominant driver under control, then it's wasted effort. I think I would just stop there and go to questions.
Perfect. If you can maybe stop share. There you go.
Yeah.
So I had one question on the impact of reforestation, and you said that it's not worth putting effort into it at the moment. Have you looked into the biotic moisture pump theory?
Biotic moisture pump
theory, yeah.
Are you referring to
I'm referring to the work of Anastasia Makareva and Viktor Gorshkov. You can, I mean, there is quite a bit of experimental evidence that they have come up with to show that what they're saying makes more sense than the current theory, because the current theory cannot even explain the rainfall over the Amazon correctly, right? Whereas their theory is able to explain it. And to me, when science cannot explain something, another scientific theory explains it, I go with the one that explains it better, usually. But it is not, it is contrary to conventional wisdom. Conventional wisdom says, don't bother. Why? Because we have to consume here, right? So there is a theory that, I mean, we sort of create our theories to promote whatever we are doing, because there's a lot of money involved in this. And so I've seen this happen time and again. This is why you look at, even in the health field, doctors never talk about changing your input, your diet, so that you become more resilient. Because there's so much money being made on the diseases.
Have to keep the sugar high, right?
Right. I mean,
we have to feed the diabetes patients a meal every a few hours.
Yeah, in fact,
That's rich
I was
in
using
starch.
the example of a doctor who was explaining how to create a mask, and he was cooking bacon to show that there is no smell there.
Mm-hmm.
It never even occurs to him that the COVID-19 is happening because of eating animals, you know. So
I'm curious about this theory you mentioned.
Mm-hmm.
So my understanding of CO2 effect on plants, one of them that would be contrary to the overall conclusion that I drew, is that water use efficiency increases under CO2 enrichment because stomatal conductance can be reduced, but still maintaining the same influx of the CO2 into the leaves for the leaf to make sugars, because there's more CO2 outside. By diffusion, there's a gradient.
Right.
And by the same token, when the perforations on the leaves are smaller, there's less water evaporating and escaping. Right. So plants need less water in a high CO2 world. But that effect is basically canceled, annulled completely when there's heating involved because of thermal stress, creating embolisms and break in water transport. So could you elaborate on the theory that you mentioned of?
So the biotic moisture pump theory argues that when you grow forests, you're actually creating a moisture pump. So what happens is that the trees take water from below ground and they send it out through the stomata, and the leaves. And along with the water comes microorganisms for raindrop formation. Okay, so when the raindrops form, it creates a low pressure zone above the forest. And that low pressure zone then causes a water circulation pattern in the atmosphere. It sucks water from above the ocean over the forest. So it creates this pump, a moisture pump. And so it changes rainfall patterns. And the forests, basically the trees that are growing, then create water over themselves. So it becomes a pump that takes salt water and turns it into fresh water.
Yes. Okay. Yeah. That effect is true, and is also analogous to one potential one effect of albedo increasing albedo in some parts may lead to decrease in rainfall by a similar effect, not exactly the same. Yes. So that is one argument that suggests that the need to invest energy to maintain forests alive may be alleviated because you would naturally get more rainfall. But the problem, more fundamental, is that when you indeed achieve forest cover, you reduce the albedo of Earth on average. And then the subsequent heating will drive all of the other negative effect that we just discussed in this presentation.
But the estimation is that the change in albedo so far has only caused about 0.2 watts per square meter of change, right? According to the IPCC. And
overall
since 1750.
It's substantially more than that.
No,
it's on the order of 3 watts per square meter.
Change in albedo?
Yes.
According to
that's not accounting for what would happen if we lost the aerosol masking effect.
No, I'm looking at the 2015 AR5. And AR5 is showing about 0.2 watts for albedo.
Can you share the screen?
I don't have it up right now. I just have my version of it, but I don't know, I can't show you. Tell you what, I'll show you that.
Drought just shared a link in the chat. I'm not sure if that's what you're looking for.
No. Okay, do you see that? So I have the reference there, so you can look that up. But basically, they're showing for CO2s, this is only the mean. I'm not showing the variation, the variance around it. So they're showing 1.68 watts for CO2, 1.7 watts for other gases like methane, nitrous oxide, HFCs, and other. They're showing 1.1 watt for the total cooling effects.
Yep.
And the surface albedo is just this. It's about 0.2 watts. And so the net is 2.3 watts according to them.
Okay, you are just referring to that. Okay, yes, I agree that the net is roughly like 2 to 3 watts range. Yeah. And the surface, that's what surface does that refer to?
That's the surface albedo around the planet. Change in surface albedo around the planet.
Okay, so far, yes, sure.
So far is 0.2 watts.
Yeah.
So that's why I'm saying, you know, forests are not a, I mean, I've had arguments about this with so many people. Forests are not a net negative, right? Because they actually are sequestering CO2 even as they change the albedo. Stop. Yeah. And so they're changing rainfall patterns, they're changing climate. You know, when you bring back forests, you are making you're making a complex change in the overall impact on the climate. But when you cut down a forest, you're making the same complex change in the opposite direction, right? So returning original forests back is not a net negative.
I don't disagree in principle about the importance of forests. I disagree with whether actively investing in reforestation is the best use of the limited time that remains and the very limited funding that's available, and whether addressing the real root cause of the problem can be a dramatic force multiplier in subsequent effort to perform reforestation in a much more efficient manner, almost without additional effort.
Absolutely, I agree with you. If we could somehow magically bring the temperature down by 1 degree, it'll be easier for us to bring back the forest that we lost.
That's right. Yeah.
Right?
Yeah.
I completely agree with that. Yeah. So maybe we have gone over time. Maybe I'll let Deborah ask questions from the audience.
Yeah, are there audiences? Maybe?
Yeah, there are about 20 people, I think, so far.
Okay.
Okay, so I'll start with a question from the QA box, and then I'll pass it to Anne, who's monitoring the chat. All right, there's a question from Miles that says, thank you for all the thoughts, research, and evidence. One suggestion for everyone is to get behind this work that Dr. Tao and the work of Dr. Rao and see it as exhibits of evidence that need to be introduced as a petition for a special grand jury. Such a petition could be made to every state attorney general. Below is a link to a YouTube video, and he provides a link here, featuring lawyer Daniel Sheehan. He talks about the legal process for a special grand jury. This methodical and legal approach to communicating exhibits of evidence where a crime has happened might get us the attention of the media and the public we need. Even a mock special grand jury would be interesting if it cannot be established that any crime has actually occurred. So I'll put it out to you guys if you want to comment on bringing legal action.
That's an interesting thought that, yeah, we can pursue legal avenues to say, you know, we need to start taking action on this. You know, we know that we have flattened the curve on the pandemic, on COVID-19 by taking action, right? But we don't see the same effective action for climate change. But we know we can do it because we are already doing something like that here.
Yeah, so COVID-19 is a very good, exercise for humanity to come together and to face a problem that's, not controllable. You cannot really shut your border, as you cannot really just shut out air flowing from another country. So it's a good experience, I think, for humanity from that perspective. As to taking legal action, yes, I'm all for it. We need people with that expertise in the community to step forward, and lead the effort. I think each of us, there's only 24 hours in a day, and we have different expertise. So it's most efficient if we devote our time to what we're best at.
Okay, we have a couple of questions in the chat here. The first is for Dr. Tao. Do you think that your mirror project to cool the planet is still an option at this time, given all of the shutdowns?
Yeah, I think COVID-19 happened at a very unfortunate moment because the conceptual framework and the development we're doing are in its initial stages, and I was scheduled to present several talks at international conferences to the physics and the bio community and climate community effectively actually like last week. But of course that didn't happen. So everything got rescheduled, canceled, and postponed by a year or two. So that's from that perspective, it's really delaying things. But I think what's comforting in a sense is to see that many countries across the continent have been able to come together and demonstrate coordinated efforts in this. And the fact that we're having a conference right now remotely also shows that we can really be very efficient in our usage of time. We can be joining several conferences in different continents during the same day. So in a sense, maybe the time lost isn't really time lost. So I think it's I think overall a net, hopefully positive experience. Okay, and for the mirror, I don't think it's too late. So the magic of the mirror is that of its simplicity. Everybody understands it. It's very easy to show kindergarten kids and elementary school children how it works in a few minutes. And because of its simplicity, it's really targeting the root cause of the heating, shortwave radiation, the colored light that's coming from the atmosphere. And we send them back without allowing them to interact further with our system. So it's a very direct interception. So by virtue of that, its effect is instantaneous up to the thermal constants of the atmosphere. So it's never too late to start. If we have an annual budget of 50 to 500 billion US dollars, we can effectively keep the climate at its current levels indefinitely, and while we do the transition to renewables. So it's not too late. We can still do it even 2 years from now, assuming crises like COVID doesn't continue to crash the economy and preventing us from putting up the aerosol umbrella up there to give us an ecosystem respite. So I think there's a lot of hope.
All right, thank you. Thank you. Dr. Rao, did you want to talk a bit about the biotic pump theory information that's in the chat right now and any of the questions related specifically to that?
Yeah, actually, what Drought has written is absolutely correct. It's a theory that, I mean, again, it's a theory that has been verified by matching it with observations in nature. That's how science actually works. You propose a theory and you match it. And if you propose a theory and you match it against science, against nature, and it doesn't match, that theory has to be thrown away, right? So the theory that we're currently using by that measure has to be thrown away because it doesn't match what's happening in the Amazon, whereas the biotic pump theory does. So that theory, it's actually a little, I mean, I don't think Makareva and Gorshko were the original proponents of the theory. It has been around, but they provided the experimental measurements to show that the theory is valid, okay? And so I have put the reference on the chat of one of their papers. I think they also have an entire website devoted to that, the biotic pump theory. So it started around 2010 is when they proposed the theory first, and people have been sort of looking into it. So they published it in the International Journal of Water. You can see the citation there. And so there have been several more peer-reviewed papers on that from the same group. I actually got to know about this theory when I saw a talk by a Brazilian scientist back in 2010, who was explaining that theory, and he was one of the co-authors. He was working with this team. Yeah, I think it's called bioticregulation.ru. Dot has the right website.
I mean, I may have briefly come across this the set of field in my reading, but I think it makes a lot of sense, right? Because forests are a prime producer of a lot of short chain carbon emissions, aerosols, and we know aerosols are very good at seeding condensation nuclei for cloud formation. So it makes sense.
So they have, I mean, the interesting part of their theory is that, you know, they're arguing that pressure is the independent variable there. It's through pressure you're changing the flow.
Okay,
so,
I see.
you know, pressure volume.
Yeah, because you have to somehow bring the moisture from somewhere, right? And you need that, because otherwise you would be just recycling in the same column without really increasing.
All right, thank you for that. We have another question. Cowspiracy is a great documentary on the impact of animal farming and greenhouse gas emissions. Any other documentaries you would recommend? So are there any documentaries about SRM? I don't know.
I think there's specific titles I can't provide off the top of my head, but there's a lot of discussions on SRM, I think. And the written documents and papers, there's tons of papers. Maybe I should prepare a list and then share with people afterwards.
Sure.
Yeah.
Are you aware of any?
I think there's sort of because traditionally SRM, solar radiation management, the field has focused on a few strategies, the most prominent of which has unintended side consequences. So artificially injecting sulfur dioxide into the atmosphere. And so the most problematic problem with that approach is that once we start doing that, we need to commit to doing that forever.
Right.
So that's one problem. The other is if we do not also remove our economy away from fossil fuels, our injection of SO2 every year has to increase year from year. And that's just simply not sustainable, for one. And as we put up more of these every year, the amount of sunlight we block out, keep away from all the ecosystem on Earth will increase also linearly or exponentially based on your economy over the years. And by the end of century, maybe we'll have a 10% reduction in the worst cases of available sunlight, which is the primary energy for all systems on Earth.
Right.
So that's another problem. And of course, if someday we failed to continue this operation, then temperature goes back, shoots up 4 or 5 degrees Celsius in the span of a few years, 5 years, within 5 years. So that's the major critique of the traditional, most prominent solution within solar radiation management community. And I think for that reason, maybe politically, it hasn't really gained much attraction. But there are other ways to do solar radiation management, for example, mirrors. And also maybe some bright silica particles for the Arctic targeted areas, for example.
Right.
All right, thank you. We have another question that came in, and then my chat box jumped away, and it took it someplace. Let's see. Okay, in simple lay terms, from your perspective, what is the most important thing individuals can do now to impact climate change?
Is that addressed to me?
Well, both of us, I guess.
Both of us.
I'm trying to get off the hook.
I wanted to ask you something, Dr. Tao.
Yes.
What if everyone started putting reflectors on their roofs? How much of an impact would that have? Mirrors on their roofs.
Okay, so if we everybody did that, we can, for the first 2 years or so, stabilize the climate. But thereafter, there wouldn't be enough space to continue that stabilization. But of course, if we somehow had a war-type mobilization during that 2 years, well, we're in one now, so why not another one? To really push for selected types of renewable energies, and then we can thereafter be okay in principle. So the amount of roof that exists is simply not enough as a long-term solution. It can, as a starter, help people ease into the idea and as an educational process. So I guess as individuals, we need to educate people around us and talk to people and just discuss the possibilities. First of all, we need to be honest about what's coming. Right. It's we don't have until the end of the century. Forget it. Right. I would be personally very happy to live to the age of 50. That would be like, what, really? So we need to be honest. Time is short. Right. But it doesn't prevent people from doing the right thing and the meaningful things. And but of course, that's a message that's pretty hard to promote, right? To the average person.
But it is a way to get people involved, right? I mean, saying if you, just like people are now shutting themselves at home, they're somehow involved in the COVID-19 pandemic and dealing with it. So if you ask people to all put even potato chip wrappers, right? The potato chip, turn it around and put it up there on your roof. They're doing something about climate that they're getting involved in it.
Yeah, of course. We need leaders like that. Maybe the arts, maybe the best art is just a whiteboard. That's purity.
Whiteboard. We talked about that yesterday with Melissa. So Melissa should be able to do that, get people to do that. So what is the estimate on the amount of built area on the planet? I've seen like 1%. No, 2%.
I think it's probably less than that. It has to be less than that, substantially less.
IPCC, I think was. Let me see. I have that somewhere here.
It could be on the of land area, on the order of single-digit percent, probably 1%. Slightly less than 1.
Yeah, it's 1% of land area. You're right.
Yeah, not of Earth. Yeah, and that's a roughly order of magnitude short of what's needed for a long-term solution.
Right.
Yeah, but of course, keep on building mirrors is not a solution. I have to make that clear, right? Mirror albedo is a way to buy time, essentially, in a affordable and ecological way. Right. And if we are smart, we can also use it for other things than just buying time. We can also use them as infrastructure to gain better control over ecosystems and to exploit the productivity of the seas, for aquaculture, and liberate land for growing forests and other ecosystem services.
Right. So, but you're talking to a community that doesn't need to eat animals, so. Because, I mean, even that is a story we've been told, which is not true.
Yeah. So, that would stop eating animal products would have roughly removed about 10% of our emissions. So it's a sizable amount.
Okay, here let me show you a couple of slides, if I may, and then we can adjourn to the next one.
Yeah.
So that is that's the land use versus land. This is from the IPCC. Okay. So the IPCC is showing 37% of the land is used for grazing and 12% for crops. And then I found this out through the work that I did with Professor Atul Jain at the University of Illinois, is that this grazing land is currently storing only 2% of the land carbon. Okay, so land carbon currently there's 2,500 gigatons of land carbon. That's the average estimate. So it's 3 times as much carbon on land than there is in the atmosphere. So this 37% is only storing 2% of the land carbon right now. Okay, and this is the land that keeps growing because we keep cutting down forests to make more grazing land. So then we looked at what happens if we shut down the killing machine, which is animal agriculture, versus shutting down the burning machine, which is fossil fuels in industry. The 2 engines of planetary destruction. So if you shut down the burning machine, you reduce 87% of the CO2 emissions annually. Okay, that works out to about 0.027 watts per square meter of radiative forcing per year. You cut down 23% of the methane, which works out to 0.022 watts per square meter. But you cut down almost 100% of the SO2. And according to IPCC at that time, it was 0.95 watts per square meter. Okay. So the total is, if you shut down the burning machine right now, you're going to cause an additional heating of 0.9 watts per square meter in 1 year. And if you shut down the killing machine, you eliminate 31% of the CO2, which is 0.009 watts per square meter. You eliminate 37% of the methane, which is 0.035 watts per square meter of heating. You then release 37% of the land back to nature. And the estimate is that that can start storing about 34.5 gigatons of CO2 per year, which is 0.06 watts per square meter, which means the total is you start cooling by about 0.1 watt per square meter. So this is my analysis on the impact of shutting down these 2 machines. If you could do that, right? Now, the shutting down the killing machine, we can do that because it's each one of us who are ordering the food, who are ordering this clothing, who are ordering the products, right? It's not up to governments. We can do that. Right? Whereas shutting down the burning machine is much harder for us.
Can you, I didn't follow all the numbers, there are quite a few. What's the percentage of CO2 based on your calculations by shutting down the killing machine?
31%.
Of the total?
Of the total, yeah. Of the CO2 alone, not the methane, not the nitrous oxide. It's 65% of nitrous oxide, 37% of the methane, and 31% of the CO2. And that comes from land use change. One of the major ones is the land use change. And secondly, it comes from the transportation for animal agriculture, the industry for animal agriculture. All of that is included in the 31%. It's a life cycle emissions analysis.
Yeah, so I was just browsing data from EPA and USDA. It seems like, according to them, I don't know if that's accurate.
They are not accurate.
Them, not accurate?
They're not accurate.
So they say agriculture, forestry, and other land use constitute 24% of global emissions.
Right. That is when you take emissions and you assign it to one sector or the other. Okay, so you say I assign it to agriculture sector, but you assign emissions to transportation sector, even though that transportation is for the agriculture sector.
I think this one is actually done such that the transportation are included, because for the US, the other alternative without combining them sets agriculture at 9%. So I think the 24% actually includes all the associated transportation costs.
Okay, so then this is global, because globally IPCC has said it's 24% for AFOLU.
And so that's one issue. So the entire agriculture industry accounts for, to very high approximation, a quarter of our CO2 emissions. And the difference between a vegan diet and an average person diet, it's on the order of 30%. So the net gain, if everybody were to make the transition, it's a 30% gain times the quarter, which is on the order of less than 10%.
Well, that's assumed. Now, again, first of all, those numbers are all based on local sensitivity analysis. So I wrote an entire white paper. I will send you a copy of that, and you can take a look at my calculations. Those are all based on local sensitivity analysis. So when you do a global sensitivity analysis, things change. Local sensitivity analysis assumes that one person is switching as opposed to an entire population switching, right? When you do a global sensitivity analysis, you release land back to nature. That is not counted in the local sensitivity analysis, and which is the biggest component, but I showed you in the shutting down the killing machine. Right. So yeah, because I'm also a systems specialist, and so I've been doing this for a long time. Anyway, thank you so much for joining us. Thank you for all this information you shared with us.
Yeah, thank you for the information that I learned from you.
Yeah, and we'll be in touch. And so tomorrow we're going to be talking to Vice Mayor Lauren Kuby, and we're going to be talking about local government needs and what we can do locally to address the situation on the ground. And so please join us, same time, 1 o'clock Pacific time. And we'll try to sort out our Zoom issues tomorrow so we can stream on Facebook as well. So thank you all very, very much. Bye.
Thank you. Bye-bye.
Thank you, everyone.